Okay, in this video, what I'm going to do is give you some summary equations and summarize the material covering analog and digital signals. Okay, and so we'll start with analog signals. And in analog signals, we have we're going to write S, which represents our signal, as a function of t. S might be, pressure in the air if the signal is a sound wave in the air. It might be a voltage if S is a signal on a wire. And typically when you have a microphone, you're going to convert a sound pressure wave in the air into a voltage on the wire. In any case, these signals are going to typically vary in time and may be continuously varying, something like this. Very complicated looking. We might also consider these signals to exist in space, in which case we can write them as a function of the spatial variable x. T is time, x is space. T has units of seconds, x has units of meters. And so if you want, you could take a snapshot in time and look at, for example, a sound wave in the air, and it would exist in space. Okay. In any case, we have no simple way, no simple equation for something like this complex wave. But what we can do is we can say, look, any complex wave like this can be broken up into a bunch of sine waves. And so what we're going to write is that an analog signal is equal to a sum of sine waves of various frequencies and that if we were to plot the amount of the sine wave, of the amount of sine wave of frequency f, we could write our signal as a function of the frequency. And so, for example, if we have only one frequency in our analog signal, where this really would be just a sine wave, a simple up and down sine wave, we'd have just one frequency, just a spike, say at frequency f0 in our signal as a function of frequency. This is called the spectral representation of the signal. Okay, and this is like the bars output in a music player on your computer. Okay, so the signal as a function of time is like the wave output of a music player, and the signal as a function of frequency is like the bars. Okay, showing different bars. Now, if you have a complex signal, it probably won't just have one wavelength in it or one frequency in it. It may have some range, okay, from F low up to F high, and that is called the bandwidth of that signal, and I denote that BW. So here's the spectral representation, and BW is equal bandwidth of that signal. So we talked about that. So I'll make little dotted lines here. Okay. So what we're going to do then is we're going to write a sine wave at a single frequency, sine. Our signal as a function of time is going to be a sine of 2 pi little t over big T, where a is the amplitude, and this should take you right back to your pre-calculus class, and capital T is the period, The amplitude may have various units, whatever the units of the wave are. So for example, if it's a voltage on a wire, amplitude would have units of voltage. If it were a sound wave in the air, it would have units of pressure. Period has units of seconds. Okay, and we can also write that the frequency is 1 over the period, and it has units of hertz, or cycles per second, or just inverse seconds, because we usually omit the cycles. And because f is 1 over t, I can write this sine wave as sine 2 pi f t. Okay. Sorry if that's a little bit messy there. Can I fix it? Run out of room here. This slows me down. Sorry. 2 pi f t. And then a parenthesis. Okay. In any case, these are two of your, and similarly we can write t equals 1 over f. In other words, they're multiplicative inverses of each other, and they are inversely proportional to one another. We can also consider the sine wave in space, in which case we're going to have, instead of a period t associated with the time variable, we're going to have a wavelength x associated with the space variable, or a wavelength lambda associated with the space variable x. So analogous to time period, we have space wavelength. Okay, and lambda is the wavelength. This is the distance of one cycle in meters if we were to take a snapshot in time, so that has the same units as x. Okay, we can make a traveling wave, and our sine wave is a function of both, or our wave is the function of both x and t. And we know that this wave will travel a distance lambda in one period. In other words, v, which is the propagation speed, is equal to, v has units of velocity, something like miles per hour. It's distance divided by time, so I'm going to put lambda over big T here. Okay, and I can add the units to this. This is meters per second velocity, and lambda is in meters, and T is in seconds. And so those two are equal. And that works out. So those are the basic equations that you need for the analog waves, or the continuously varying waves. Now I'm going to go to digital signals. And these, we don't have a real nice way. In the same way with analog signals up here, we don't have a real nice way usually of writing down the function s of t, but very often we can write it as maybe it's a sum of a few sine waves or just one sine wave, or it might be a very complex composition of a continuously varying number of frequencies. Digital signals are similarly, we don't have a real nice way of writing them down. There's no simple equation. And our digital signals typically look something like this. Let me go ahead and make it look pretty with a red. Maybe we've got some zeros and ones here. Maybe we label this 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, something like that. And this is the time axis. Let me get rid of some of this other stuff here. Okay, so this is the time axis, and this is our signal as a function of t. Okay, we don't have a very nice way of writing that down, and so we just deal with things like t sub b. This is the bit period. It has units of seconds. We have the bit rate, r sub b. It has units of bits per second, or bit per second, like that. And we have the fundamental relationship, TB is 1 over RB, RB is 1 over TB, almost exactly the same as up above when we were doing analog signals and we're looking at the frequency and the period. The bit rate acts like the frequency, in other words, here. We can also write LB, the length of a bit, and it's going to act more or less like the wavelength, and it has units of meters. And what we can do is we can say that the propagation speed is equal to the length of a bit divided by the bit period. Or, if I want, I can write the length of the bit times the bit rate. Okay? Very similar to the equation up here. Propagation speed is lambda over t. As a matter of fact, I should go ahead and use the fact that the frequency is 1 over the period in this equation up here and write that this is also lambda f. Okay? I can make an equal sign there. Okay. Finally, the very last thing I'll show you is that we can also define NB, the number of bits, and this may be the number of bits in a file, it may be the number of bits in a frame, for example an Ethernet frame, and the number of bits is equal to the bit rate times the amount of time. Okay, so for example, you have bits, units of bits on the left, you have bits per second in your bit rate, and you have seconds in your time. So you can see the units work out, and this is a way of calculating the amount of time it takes to send a file. So for example, if we solve for t, we get NB over RB, and we see that the time it takes to send a file is directly proportional to the size of the file. So you double the size of the file and you double the time it takes. But it's inversely proportional to the bit rate because as you increase the bit rate, it takes less time to send. So for example, you double the bit rate and you cut the transmission time for that file in half. Okay, these are the fundamental equations that you need for doing the first homework or two in this class. So hope this helps.